Welcome back to the deck of the midnight vessel. Tonight, the air has changed. There is a cold in it that was not there before, clean and sharp and very old, the kind of cold that comes not from the season, but from somewhere much further away, somewhere that has not seen sunlight in 10,000 years. Tonight, the ship is sailing toward the ice. A glacier begins as something almost impossibly delicate. A single snowflake, falling through still air, is a structure of extraordinary complexity, a six-sided lattice of ice crystals, no two ever identical, built in the few seconds of its descent by the precise temperature and humidity of the air it passes through. It lands, it joins other snowflakes, and if the conditions are right, if the winters are cold enough and long enough, and the summers short enough that the snow does not fully melt, it begins a transformation that will take centuries to complete. The soft, light powder of new snow is compressed by the weight of the snow falling above it, its delicate crystal structure collapsing and recrystallizing into something denser and harder. This intermediate stage is called firn, a granular, compacted snow that has survived at least one full year without melting. As more snow accumulates and the pressure increases, the air pockets between the firn crystals are slowly squeezed out. The firn becomes glacial ice, a substance so compressed and so old that it is fundamentally different from the ice in a glass of water. Glacial ice is blue, not in the way that water sometimes looks blue, but deeply, inherently blue, because the compression has removed nearly all the air bubbles that scatter white light, and the dense ice absorbs the red end of the visible spectrum, leaving only blue to be reflected back to the eye. The blue of a glacier is the color of time made visible. The deeper and older the ice, the deeper the blue. A crevasse wall in an ancient glacier is a shade of blue so pure and so deep that people who have seen it often struggle to describe it as a color at all. This transformation from snowflake to firn to glacial ice takes between decades and centuries, depending on the accumulation rate and temperature. In Greenland, where snowfall is relatively light, it can take 200 years for surface snow to become true glacial ice. In Antarctica, where the ice sheet at its deepest is nearly 5 kilometers thick, the ice at the very bottom fell as snow more than 800,000 years ago. It has been compressed and buried and carried slowly downward by the weight of everything above it for longer than our species has existed in its current form. When a drill pulls a core of that ice to the surface and a scientist holds it in her hands, she is holding 800,000 years of unbroken atmospheric history. Every layer is a year, every bubble is a breath of ancient air, sealed and preserved, waiting. A glacier is not a static object. Even as it accumulates snow at the top, it is constantly losing ice at its edges and terminus carving icebergs into the sea, melting at its base where geothermal heat meets the ice from below, sublimating at its surface where dry winds carry ice molecules directly into the air, without melting them first. A glacier in balance loses exactly as much ice as it gains. It is a system in dynamic equilibrium, perpetually building and perpetually shedding, maintaining its form across centuries through a constant exchange that looks, from the outside, like stillness. This is perhaps the first and most important thing to understand about glaciers. What appears to be frozen is, in fact, always moving. There are approximately 200,000 glaciers on Earth today, covering roughly 10% of the planet's land surface. They hold about 69% of all the fresh water on Earth, more fresh water than all the world's rivers, lakes, and groundwater combined. The ice sheets of Antarctica and Greenland alone contain enough water that, if they were to melt entirely, global sea levels would rise by approximately 65 meters. Every coastal city on Earth would be submerged. Every delta, every estuary, every low-lying plain where civilizations have gathered since the beginning of agriculture would disappear beneath the sea. The ice is not merely scenery, it is the reservoir on which the shape of the inhabited world depends. The cold settles deeper around the ship now, and somewhere ahead in the dark, the first pale shapes of ice are beginning to appear on the water. We have watched the snowflake become fern, the fern become ice, the ice becomes something that holds 800,000 years of memory in its blue and silent depths. In the next passage, we watch the glacier do something that seems impossible for something so vast and so heavy. We watch it move. A glacier moves. Not in the way water moves, not in the way wind moves, not in any way that is perceptible to a person standing on its surface on any given day. But move it does, grinding forward under its own immense weight, reshaping the bedrock beneath it, carving the landscape with a patience and a thoroughness that no other force on earth can match. The valleys we walk through, the lakes we sail on, the dramatic peaks that define so many of the world's most beautiful places, most of them were made by ice in the slow and irresistible work of glaciers that have long since retreated or disappeared entirely. Glaciers move through two primary mechanisms, working simultaneously. The first is internal deformation. The ice itself flows in a process that seems impossible for a solid, but makes sense when you consider that ice under sufficient pressure becomes slightly plastic, its crystal structure allowing individual layers to slide incrementally past each other like a very slow, very cold liquid. The second is basal sliding at the base of many glaciers. The enormous pressure of the ice above lowers the melting point of the ice at the bottom, producing a thin film of meltwater that acts as a lubricant between the glacier and the bedrock. The glacier, in effect, floats on a skin of its own melt, sliding forward on the very water it creates by its own weight. It is an elegant and slightly paradoxical mechanism. The glacier melts in order to move, and moves because it melts. The speed of this movement varies enormously. Most mountain glaciers advance somewhere between a few centimeters and a few meters per day, fast enough to be measurable, slow enough to be invisible. The Jakobshavn Glacier in Greenland, one of the fastest moving glaciers on Earth, advances at rates of up to 46 meters per day, fast enough that a person standing at its terminus could watch it move, slowly but unmistakably, toward them. Most glaciers, though, keep their movement hidden, working in a timescale that the human lifespan is too short to witness directly. The work a glacier does to the landscape beneath it is among the most dramatic sculpting forces in geology. At the base of the glacier, rock fragments become embedded in the ice boulders, pebbles, fine grit, turning the glacier's underside into something like an enormous sheet of sandpaper dragged across the bedrock for thousands of years. This process, called glacial abrasion, smooths and polishes the underlying rock, leaving behind long parallel scratches called striations that geologists can read like a compass, pointing in the direction the ice once moved. In places where harder rocks were plucked from the bedrock and dragged forward, the glacier leaves behind a characteristically asymmetric landform, smooth and gently sloping on the up-glacier side where the ice rode over it, steep and jagged on the down-glacier side where chunks were torn away. These are called roches, moutonnes, sheep rocks, named for their fancied resemblance to a grazing flock. The valleys that glaciers carve are fundamentally different in shape from those carved by rivers. A river valley is V-shaped, cut by the narrow incision of flowing water working downward. A glacial valley is U-shaped, broad and flat-bottomed and steep-sided, scoured out by the full width of a moving ice mass that grinds not just downward but sideways, widening and deepening its corridor simultaneously. When a glacier retreats and the ice is replaced by seawater, a U-shaped glacial valley becomes a fjord, the dramatic, deep-walled inlets of Norway, Chile, New Zealand, and Greenland that are among the most spectacular coastal landscapes on Earth. Every fjord in the world is a glacier's autobiography, written in rock and water, still legible thousands of years after the ice has gone. Glaciers also carry material. As a glacier advances, it picks up rocks and soil and incorporates them into the ice, transporting them sometimes hundreds of kilometers from their origin. When the glacier retreats or melts, it deposits this material in characteristic formations, long ridges of mixed debris called moraines that mark the glacier's former extent, and giant boulders called erratics left stranded on bedrock of a completely different geology. Geologists in the 19th century used these erratics as evidence of past glaciation, tracing the boulders back to their source and mapping, from the stones alone, the roots of ice sheets that had vanished 10,000 years before. The glacier was gone, but it had left its itinerary behind. The ship moves slowly through water that was once covered by ice a kilometer thick. Beneath the hull, the bedrock still bears the long parallel scratches of the glacier that crossed it, a signature left in stone by something that will never return to this particular place. In the next passage, we go deeper into the glacier itself, not to its surface or its base, but into its interior, where the ice holds something more extraordinary than rock or water. It holds time. Deep in the interior of Antarctica, far from any coast, in a place where the temperature rarely rises above -30 degrees even in summer, scientists drill. They drill slowly, carefully, extracting cylinders of ice a meter at a time from depths that represent not meters but millennia. The core that comes up is handled like a living thing, kept frozen, labeled precisely, transported in insulated containers to laboratories where it will be sliced and analyzed and read, the way a scholar reads an ancient manuscript for everything it contains. What it contains is nothing less than a continuous record of Earth's atmosphere stretching back 800,000 years. The mechanism of this record is the air bubble. As snow accumulates and compresses into glacial ice, the air between the snow crystals is gradually sealed off, trapped in tiny pockets, isolated from the atmosphere above, preserved at the exact composition it had on the day the snow fell. Each bubble is a sample of ancient air, a sealed vial of the atmosphere from a specific moment in the past, held in suspension by the surrounding ice. When scientists crack open a section of ice core and release those bubbles, they are breathing air that last moved freely through the world before humans existed, air from a time when mammoths grazed the Siberian steppe and the Sahara was a savanna. The act of opening an ice core is, in a very literal sense, an act of time travel. From these bubbles, scientists have reconstructed the history of Earth's climate with a precision that no other archive can match. They can measure the concentration of carbon dioxide and methane in the atmosphere at any point in the last 800,000 years, track the rise and fall of global temperatures across 8 complete ice age cycles, identify the chemical signatures of specific volcanic eruptions, and even detect traces of industrial pollution from the 20th century, a thin dark layer near the surface of modern cores, as legible as a date stamp. The ice does not editorialize, it does not select or emphasize or forget. It simply records, layer by layer, year by year, everything the atmosphere was doing at the moment each snowflake fell. It is the most honest archive humanity has ever found. But the ice preserves more than air. In 1991, 2 hikers in the Alps discovered the body of a man emerging from a melting glacier near the border of Austria and Italy. He had been there for 5,300 years. Ötzi the Iceman, as he came to be known, was so perfectly preserved by the cold and the ice that scientists were able to determine not only his age and his diet and his health conditions, but the contents of his last meal, eaten roughly 30 to 60 minutes before his death, and the precise sequence of injuries that killed him. He had been shot in the shoulder with an arrow, which severed a major blood vessel. He bled to death on a mountain pass in the Copper Age, fell into a hollow in the glacier, and was covered by snow within hours. The ice kept him exactly as he was for more than 5 millennia, until the mountain decided it was time to let him go. Ötzi is the most famous of the glacier's preserved subjects, but he is far from alone. As glaciers around the world retreat, they are releasing things they have held for centuries, the bodies of mountaineers who disappeared decades ago, the equipment of soldiers from World War I buried by avalanches on the Alpine front, ancient forests that were overrun by advancing ice thousands of years ago and are now emerging, still upright, their wood preserved by the cold. In Canada, retreating glaciers have revealed artifacts of First Nations peoples, wooden tools, leather garments, woven baskets that had been sealed in ice for centuries and are now being recovered and returned to the communities whose ancestors made them. The glacier gives back what it takes, eventually, on its own timetable and in its own order. There is a particular kind of wonder in the idea that the ice remembers, that every snowflake that has ever fallen in certain cold places has been retained, compressed, archived, added to a record that grows one layer thicker each year. The glacier does not choose what to preserve. It does not curate or select. It simply receives what falls upon it and holds it, faithfully and without judgment, for as long as the cold persists. There is something almost tender in that, a patience so vast it makes the whole of human history look like an afternoon. The cold air moves across the deck of the midnight vessel, carrying with it the faint mineral scent of very old ice. We have looked into the glacier's archive and found 800,000 years of atmospheric history, a Copper Age man preserved in the mountain, and forests that outlasted the ice that buried them. In the next passage, we descend even further below the glacier itself, into the hidden world that exists in the darkness beneath the ice. Beneath the glaciers, in the cold and the dark and the crushing weight of kilometers of ice, there is a world that has been cut off from the surface for longer than human civilization has existed. No sunlight reaches it, no weather touches it, no sound from above penetrates its silence. And yet it is not empty, not dead, not inert. It is one of the strangest and most isolated ecosystems on Earth, a place where life has found a way to persist under conditions that should, by every reasonable expectation, make life impossible. Under the Antarctic ice sheet, at a depth of nearly 4 kilometers, lies a lake. Lake Vostok is not a small body of water. It is approximately the size of Lake Ontario, 250 kilometers long, 50 kilometers wide, with depths reaching over 800 meters. It has been sealed beneath the ice for somewhere between 15 and 35 million years, isolated from the surface atmosphere since before our earliest hominid ancestors walked the African savanna. The pressure of the ice above it keeps it liquid, despite temperatures well below the normal freezing point of water, a phenomenon called pressure melting, the same mechanism that allows glaciers to slide on their own melt. It is a dark, cold, pressurized lake that has been waiting in absolute isolation for longer than our genus has existed. In 2012, a Russian drilling team broke through the ice ceiling into Lake Vostok, the culmination of decades of drilling through nearly 4 kilometers of ice. The water that rushed up into the borehole was the first contact between that lake and the surface atmosphere in millions of years. Analysis of the water and ice samples retrieved has found evidence of microbial life, bacteria and other microorganisms that have been adapting to the cold, the dark, and the pressure of their isolated world for an almost incomprehensible span of time. What they have become, cut off from the rest of life on Earth for 30 million years of independent evolution, is a question that scientists are still working to answer. Lake Vostok may contain organisms that exist nowhere else on the planet, life forms shaped by conditions so extreme and so prolonged that they represent, in effect, a separate experiment in what life can be. Lake Vostok is the largest of Antarctica's subglacial lakes, but it is far from the only one. Scientists have identified over 400 subglacial lakes beneath the Antarctic ice sheet, connected in some cases by subglacial rivers that flow through channels carved in the bedrock. Water moves through this hidden network, driven by subtle differences in pressure and geothermal heat, linking isolated pockets of liquid in a slow, dark circulation that has been running beneath the ice entirely unobserved for millions of years. The Antarctic continent, which appears from the surface to be nothing but a featureless white plain, conceals beneath its ice a complex hydrological system as intricate as any on the surface of the Earth. We are only beginning to map it, and every new survey reveals more than the last. The ice itself, in its deepest and oldest layers, also harbors life. Bacteria have been found alive in ice cores from depths representing hundreds of thousands of years of burial organisms that have been frozen, not dead, waiting in metabolic suspension for conditions that may never return. They repair their own DNA at extraordinarily slow rates, making corrections to the molecular damage accumulated over millennia at a pace that would be meaningless in any other environment. They are not thriving, they are enduring, existing at the absolute minimum threshold of what it means to be alive, conserving every possible unit of energy, persisting in a state that is closer to paused than to living. They have been paused, some of them, for longer than our species has existed. And when warmed and given nutrients in a laboratory, some of them wake up. The implications of all this extend beyond Earth. Europa, one of Jupiter's moons, is believed to harbor a vast liquid ocean beneath a shell of surface ice, kept liquid by the tidal heating generated by Jupiter's immense gravity. Enceladus, a moon of Saturn, is known to be actively venting water vapor and ice particles from a subsurface ocean through cracks in its icy shell. If life can persist in the subglacial lakes of Antarctica, in the cold and the dark and the pressure, cut off from sunlight and the surface atmosphere for tens of millions of years, then the conditions under the ice of Europa or Enceladus are not obviously less hospitable. The world beneath the glacier is, in this sense, a proof of concept, a demonstration that the universe may be more full of life than the silence suggests. A glacier is not silent. This is one of the first things people notice when they stand close to one, the sounds it makes, unexpected and varied, and somehow both alien and deeply familiar at once. There are the low groans of ice under compression, moving through the body more than the ears, felt as much as heard. There are sharp cracks that split the air without warning, the sound of new fractures propagating through the ice at speeds approaching the speed of sound. There are the long, resonant creaks of a glacier adjusting its weight, and the hollow musical tones of meltwater running through channels hidden deep within the ice, and the hiss and murmur of 10,000 small streams crossing the surface in summer. A glacier in motion is a symphony of physics, every sound a record of forces too large to see and too slow to watch, made briefly audible in a moment of release. The most dramatic sound a glacier makes is the calving of an iceberg. When a glacier reaches the sea, its terminus extends out over the water, buoyed partially by the ocean beneath it, until the stress becomes too great and a section fractures and falls. The sound of a large calving event carries for kilometers across the water, a deep, rolling thunder followed by the crash of the ice hitting the sea and the long subsiding roar of the waves it generates. Glaciologists who study calving events describe them as some of the most powerful sounds in nature, comparable in energy to a moderate earthquake, which is in fact what they are sometimes classified as. The seismic stations that monitor earthquakes around the world regularly record glacial calving events as far as thousands of kilometers from their source. The glacier announces its losses to the whole planet. The blue color of glacial ice, which we touched on in the first passage of this voyage, has its own physics worth understanding more fully. Ice absorbs light across the visible spectrum, but it absorbs red light more efficiently than blue. In a thin layer of ice, a single cube, a window pane of frost, this absorption is too slight to notice, and the ice appears clear or white. But in a glacier, where light must travel through meters or tens of meters of ice before being reflected back, the cumulative absorption of red wavelengths becomes significant. The deeper the light penetrates before being scattered back, the more red has been removed, and the more intensely blue the returning light appears. The blue of deep glacial ice is therefore a measure of depth, of how far the light has traveled into the ice and back. It is color as distance, color as time. Crevasses, the deep fractures that split glacier surfaces, form where the ice is under tensile stress, typically where it moves over a rise in the bedrock or where different sections travel at different speeds. The walls of a crevasse are among the most visually extraordinary things in the natural world, sheer, glassy plains of blue ice descending into a darkness that grows deeper and bluer until the light fails entirely. Some crevasses are shallow enough to see the bottom. Others descend 30, 40, 50 meters before narrowing to nothing. The deepest ones have no visible bottom at all. They are windows into the interior of the glacier portals through which the blue light of deep time is briefly visible from the surface. Meltwater on a glacier surface creates patterns of extraordinary beauty. Streams carve sinuous channels into the ice, their paths controlled by the subtle topography of the glacier surface. Moulins, vertical shafts through which surface meltwater plunges into the glacier's interior form, where a stream finds a crack and begins to widen it, eventually creating a cylindrical borehole that can be meters across and descend hundreds of meters into the ice. The sound of water falling into a moulin, a rushing, echoing roar rising from the blue depths, is one of the most haunting sounds in the glacial environment, a reminder that even the most apparently solid things are, at the surface, always melting. Ice also speaks in color beyond blue. Dust layers, carried by ancient winds, appear as dark bands within the glacier's stratigraphy. Volcanic ash from eruptions thousands of years ago shows up as distinct grey horizons, visible in crevasse walls and ice cores. Algae that colonize the surface of melting ice can turn vast areas of a glacier pink or red, a phenomenon called watermelon snow, known to mountaineers for centuries, the darker pigmentation accelerating melting by absorbing more sunlight. The glacier is not simply white. It is a canvas on which the history of the atmosphere has been painting in layers for hundreds of thousands of years. 20,000 years ago, the midnight vessel could not have sailed where it sails tonight. The sea itself would have been lower by roughly 120 meters because so much of the world's water was locked in ice. Ice sheets stretched across North America as far south as what is now New York City, across northern Europe to the edge of what is now the English Channel, which was then not a channel at all but a frozen plain across which animals and people could walk from Britain to the continent. The world was colder, drier, and far more dominated by ice than anything alive today has ever experienced. We are living in the warm interval between ice ages, a period called the Holocene, and the glaciers we see today are the retreating remnants of a vast cryosphere that once covered nearly a third of the Earth's land surface. The last ice age did not end all at once. It retreated in pulses millennia of gradual warming interrupted by sudden cold reversals, driven by slow changes in Earth's orbit and amplified by ocean and atmospheric feedbacks. One reversal, called the Younger Dryas, began about 12,900 years ago when a pulse of glacial meltwater flooded the North Atlantic, disrupting the ocean circulation that keeps northern Europe warm. Within decades, temperatures dropped by as much as 10 degrees. Then, 11,700 years ago, the cold ended abruptly and warming resumed. The whole episode lasted barely 1,200 years. In geological time, it was a blink. In human experience, it was a civilization. The retreat of the glaciers after the last ice age reshaped the human world profoundly. As the ice pulled back from Europe and North America, it exposed vast new landscapes of bare rock and glacial sediment, colonized first by tundra, then by forest, then by the diverse ecosystems that support human life today. The Great river systems of the northern hemisphere were carved or dramatically reshaped by glacial meltwater. The fertile plains of the American Midwest were built from glacial deposits, their deep, rich soils the ground-up product of millennia of glacial abrasion. The breadbasket of the modern world is, geologically speaking, a gift from the ice. The glaciers that remain today are retreating, not in the slow orbital rhythm of ice age cycles, but at a rate and consistency that reflects something new in the atmosphere, a warming signal that has been accelerating since the middle of the 20th century and shows in the ice with the same clarity as a volcanic horizon or a layer of industrial soot. Glacier National Park in Montana was named for the approximately 150 glaciers present when it was established in 1910. Today, fewer than 30 remain, and projections suggest that by 2030 or 2040, the park may have no glaciers at all, a possibility the Park Service has quietly begun to acknowledge in its interpretive materials. The name will remain after the ice is gone, a monument to something that was there and is no longer. In the Himalayas, glaciers feed the rivers, the Ganges, the Indus, the Yangtze, that provide fresh water to billions of people across South and East Asia. The glaciers act as natural reservoirs, storing winter precipitation as ice and releasing it slowly through the summer as melt, smoothing the seasonal variation in river flow and providing water to lowland communities during the dry months when rainfall alone would not be sufficient. As those glaciers shrink, the immediate effect is often an increase in river flow, more meltwater than usual, but the longer-term consequence is a reduction as the reservoir empties faster than it fills. The glaciologists who study these systems use the term peak water to describe the point at which meltwater contribution begins to decline, a point that many Himalayan glaciers are already approaching or have already passed. Beyond peak water lies a future in which the seasonal buffer is gone and the rivers run lower in summer than they have in thousands of years. And yet the glacier does not mourn. It does not know it is retreating, does not register the change in its own extent from one decade to the next, does not carry any awareness of what it is losing or leaving behind. It simply responds to temperature, as it always has, advancing when cold accumulates faster than warmth can melt, retreating when the balance tips the other way. It has done this many times before, across the long rhythm of ice ages and warm intervals, across a timescale that makes the current moment look very small indeed. The awareness of the loss belongs entirely to us. The grief, if there is grief, is a human thing felt by the species that learned to read the ice and now watches it disappear before it has finished telling its story. The midnight vessel has reached still water at last, a quiet bay ringed by the pale shapes of ice, their surfaces catching the faint light of the night sky and returning it as something softer, something ancient. The air here is the coldest of the voyage, and it carries a quality that is difficult to name, a cleanness, a stillness, a sense of having arrived at a place that exists outside the ordinary rhythm of time. This is what glaciers do to the people who stand near them. They make the present tense feel provisional. They remind you without saying a word that the world is older than anything you have lived through and will continue long after everything you know has settled into sediment. The phrase "frozen in time" is usually meant metaphorically, a moment preserved, a memory unchanged, something held exactly as it was. But in the presence of a glacier, the phrase becomes literal in ways that the metaphor never quite captures. The ice core pulled from 4 kilometers beneath the Antarctic surface contains air that was sealed in the year your great-great-grandmother's grandmother was born, and the year before that, and the year before that, stretching back 800,000 years without a gap. Ötzi the Iceman ate a meal of ibex meat and einkorn wheat 30 minutes before he died, and 5,000 years later a scientist catalogued the contents of his stomach. The ancient forests emerging from retreating alpine glaciers are still standing, their wood intact, their roots still in the soil where they grew before the ice came for them. The glacier does not preserve selectively. It keeps everything indiscriminately, with a fidelity that no human archive has ever matched. There is a glacier in Greenland called Jakobshavn that has been flowing into the sea for tens of thousands of years. Every day it advances 46 meters and carves enormous icebergs that drift south into the North Atlantic shipping lanes. It was an iceberg from a glacier, very much like this one, that the Titanic struck in April 1912, a fragment of Greenlandic ice that had been drifting south for 2 or 3 years. The ice it was made of had fallen as snow on the Greenland ice sheet perhaps 10,000 years before it met the ship. It had waited, compressed and blew through the entire span of recorded human civilization, and then drifted out to sea at precisely the wrong moment, or, depending on how you read the story, precisely the right one. What is it that makes glaciers so affecting? Partly it is the scale, the sheer immensity of a body of ice that has been in motion longer than our species has existed, that contains within its blue depths a record making all of human history look like a footnote. But scale alone does not produce the particular feeling that glaciers reliably generate. The difference, perhaps, is the visibility of time. A glacier is not just large, it is legibly old. Its layers are visible, its history is readable, its age is written in the color of the ice, and the depth of the crevasses and the striations in the rock beneath. You are not imagining its age, you are looking at it. Glaciologists who spend careers studying the ice often speak about it with a tenderness not typical of scientific discourse. They name glaciers, they mourn the ones that disappear, they describe returning after years away and finding a glacier diminished the way one might describe a friend found frail after a long absence. The grief that glaciologists feel about the ice is a form of knowledge and understanding earned through years of attention of what is being lost and what will not come back in any human time frame. And yet the ice that remains is still here tonight, The glaciers that are retreating have not yet retreated. The archives have not yet been fully opened. The subglacial lakes still wait in their dark, pressurized isolation. The blue still deepens in the crevasse walls, and the carving glaciers still thunder their losses into the sea, and the ice cores still hold their ancient air in bubbles that have not yet been broken. What is here is still here, and what is here is extraordinary, a record of the world so complete and so faithful that no library built by human hands has ever come close to matching it. The ice remembers everything. Let your body settle now into the stillness that the ice has brought to this corner of the voyage. The cold that comes off the glacier is the cold of 800,000 years of winter, held and released slowly into the air above the ship. Breathe it in if you can feel it, that particular quality of cold that is not unpleasant but clarifying, that makes the mind very quiet and the body very still. This is the cold that the glacier has always offered to whatever stands near it, a stillness borrowed from deep time, a quietness that has nothing to do with the noise of the present moment and everything to do with the long, patient, indifferent passage of the world. The ice holds its watch in the dark. The ship is still. The night is yours. Good night.